Particle motion. How do particles behave in the 4 states of matter? This presentation will help you understand the Matter for a Learning target, understand the relationship of the motion of particles to the states of matter for gases, liquids, and solids. Although the learning target focuses on the 3 main states of matter, we will also take a small look at the 4th state of matter. We define matter as anything that has mass and takes up space. This could include the laptop you're using or the air you're breathing. All matter is made of small particles, which are atoms or molecules. These particles are always in motion, and because they are in motion, they often bump into each other. So, how fast these particles are moving and how much they are attracted to each other will determine the state of matter. You're probably familiar with the 3 main states of matter, solid, liquid, and gas, but there is also a 4th state of matter, plasma. This phase only occurs at very high temperatures. We are going to talk about how the particles are moving within each of these states of matter in just a moment. But first, the Kinetic Molecular Theory. This theory provides a basis of particle movement. It states that all matter is composed of tiny particles. These particles are in constant random motion. The particles collide with themselves and the walls of their container if they are in a container. The more energy the particles have, the faster they move. This point will be essential to our understanding of the states of matter. And the attraction of the particles decreases with an increase in distance. So particles are less attracted to each other if they are farther apart. So what does this word kinetic mean anyway? Since it is part of the Kinetic Molecular Theory, we should have a general understanding of what the word means. Kinetic refers to motion, so anything in motion has kinetic energy. According to the Kinetic Molecular Theory, all particles are in constant motion, so all particles have kinetic energy, or energy that comes from motion. Now that we have a general idea about what the Kinetic Molecular Theory is, let's see how it relates to the states of matter. Imagine we have a marble, and we drop this marble in a bottle. What would happen, if anything, to the shape and size of the marble? What if we change the bottle to make it larger? Would that affect the size or shape of the marble when we dropped it in the bottle? No, nothing happens, does it? The marble will keep the same size and shape, even in the bottle, because it is a solid. As you have learned, a solid is the state of matter that has a definite shape and volume. The particles in a solid are very close together, and there is a strong attraction between them. They are tightly packed. According to the Kinetic Molecular Theory, the particles in a solid move because all particles are in constant motion, but they do not move fast enough to overcome the attraction between them. They have a low amount of kinetic energy. As you can see in this diagram, each particle vibrates slightly in place, but it stays in its general position. Particles in a solid have less energy than particles in other states. This is the state of matter with the lowest amount of energy. Let's consider another scenario. What do you think would change about soda if you poured it from a can into a glass? Would the volume of the soda be different? Would the taste of the soda change? Liquid is the state of matter that has a definite volume, but no definite shape. This means that if you put it into a different container, the amount of space it takes up will not change, but the shape of the liquid will change to take on the shape of its container. So liquids can change shape, but the volume stays the same. The particles in a liquid move faster than those in a solid. They are able to overcome some of the attractions between them, and so they can slide past each other. This results in the ability to take the shape of whatever container it is in. The particles in liquids have more energy than solids, which is why they are able to move more. The 3rd state of matter is a gas. A gas has no definite shape or volume. This means that they will spread out to fill whatever container they are in. The particles of a gas move quickly, which allows them to break away from each other. The attraction between particles is much lower. The amount of empty space between gas particles can change. The particles can be widely separated, or they can be compressed to be tightly packed together. As I mentioned, the particles of a gas have less attraction between them than do particles of the same substance in the solid or liquid state. And the reason why they can move more is because they have more energy than solids or liquids. Here we are comparing the liquid and gas state of the element bromine. Which one represents the liquid state and which one represents the gas state? Hopefully you determined that the one on top was the gas. The particles are more widely spaced and moving faster than the sample on the bottom, which represents the liquid state. If you want to check out this website at some point, it presents a cartoon that summarizes the motion of particles in the three states of matter. It might be something worth checking out later. You can just copy and paste that link into a new website. The final state of matter is plasma. You might not have heard of this phase before because it is not achieved very often by most substances. Plasmas have the highest energy of all the states of matter. The energy is so high that it not only exceeds the attractive forces between molecules, but it also exceeds the attractive forces that hold atoms together. As a result, the molecules are broken down into their parts, which include protons, neutrons, and electrons. The resulting material often carries a positive or negative charge with it because of the breakdown of the atom. Some examples of plasma include lightning, neon lights, the northern lights which can be seen around Alaska, and stars. These are all materials that have exceptionally high amounts of energy, so much so that it is sometimes hard to still consider them as being matter. But remember, as long as they have mass and take up space, they are matter. At this point, take a moment to draw what the particles would look like for a solid, liquid, and gas in the circle diagrams on your note taker. Once you have done this, continue with the video. Hopefully your diagrams look something like these, with the particles closely spaced for solids and getting farther apart for gases. So we have talked about what the particles are like in each of the states of matter. We are now going to look at what happens to those particles when they go through a phase change, when they change from one state to another. Imagine being outside on a hot day trying to eat a frozen juice bar. In just a few minutes, the juice bar starts to melt, it drips all over your hand and down onto the sidewalk, and soon becomes a liquid mess. As the juice bar melts, it goes through a change of state, or what we call a phase change. A phase change is when a substance goes from a solid to a liquid, or liquid to gas, or vice versa. There are 4 main phase changes, but 2 additional, less common ones that we will also explore. Let's take a closer look at the type of phase changes and how the kinetic molecular theory is related to phase changes. As we described earlier, particles in liquids have more energy than particles in solids, and particles in gases have more energy than particles in liquids. Therefore, to change a substance from one state to another, you must add or remove energy in order to get the particles to either speed up or slow down. Realize that when a phase change occurs, the substance itself is not changing. It's just its state of matter is changing. As water turns to ice, it is still made of the same thing, H2O. It is just now a solid instead of a liquid. The first type of phase change we will look at is melting, sometimes called liquefaction. This is when a solid turns into a liquid. In order for this to happen, energy has to be added to the substance. As the energy of the solid increases, the temperature increases, and the particles will move faster. Once a certain temperature is reached, the particles in the solid will start to slide over one another, breaking some of those attractive bonds, and the solid will melt into a liquid. The temperature at which a substance changes from a solid to a liquid is the melting point of that substance. Melting point is what we call a physical property, and is specific to a particular substance. Each substance has its own melting point. We will explore melting and boiling points more in a later unit. Another phase change is freezing, or solidification. This is when a liquid turns into a solid. In this case, energy must be removed from a liquid. This can happen by decreasing the temperature. A decrease in energy and temperature will cause particles to slow down and begin locking into place. The bonds of attraction will increase. When a certain temperature is reached, the liquid will freeze into a solid. Freezing is the reverse of melting, so freezing and melting occur at the same temperature. For instance, if water freezes at 0 degrees Celsius, it will also melt at 0 degrees Celsius. The difference will be whether energy is being added or removed from the system. That will determine whether it freezes to a solid or melts to a liquid. Boiling, also known as evaporating, is when a liquid turns into a gas. In this case, energy is added to a liquid by increasing the temperature. This causes the particles in the liquid to move faster. When the particles move fast enough, the attraction between them decreases and they are able to break away from the other particles, evaporating into a gas that has a high amount of energy and is able to spread out. The last common type of phase change is condensation. This is when a gas moves into the liquid state. This happens when energy is removed from a gas. The particles start to slow down, the attraction between them starts to increase and overcomes their motion. The particles will then clump together, forming a liquid, or what we sometimes call condensation. One of the more uncommon phase changes is sublimation. In this type of phase change, a solid goes directly to a gas without becoming a liquid first. Solid carbon dioxide, also known as dry ice, is the most common substance to sublimate. It goes straight from a solid to a foggy-looking gas. Sublimation can occur under high temperatures and low pressure, but it is very rare and does not occur in most substances. The other uncommon phase change is deposition. In this change, a gas changes directly into a solid without first becoming a liquid. This occurs often in clouds when water vapor, what we call water when it is in a gas state, becomes snow without first becoming water. Another example of deposition is soot. These particles rise from fire and chimneys as a gas, but then when they come into contact with the walls of the chimneys, energy is removed, the gas cools, the particles slow down, and the gas changes directly to a solid state. Again, though, deposition is a type of phase change that does not occur in most substances. This diagram shows how energy changes when moving from one state to the next. To move from a solid to a liquid to a gas, energy must be added. As a result, the particles move more and attractions between them are broken. To move in the opposite direction, from a gas to a liquid to a solid, energy has to be removed. The particles start to move less and attractions become stronger. Adding or removing energy can also be viewed as adding or removing heat, which is a form of energy. When we add heat to ice, it melts. When we add heat to a liquid, it evaporates. If we remove heat from water vapor, it will condense into a liquid. And if we remove heat from water, it will freeze. This is true for any substance, not just water. Hopefully you have figured out the relationship between energy, temperature, and particle movement, but let's add to your understanding. When most substances lose or gain energy, one of two things happens to the substance. Either its temperature changes, or its state of matter changes. These things cannot happen at the same time. The temperature will only increase up to the melting or boiling point of a substance. At that point, any additional energy is going into changing the substance's state of matter, from a solid to a liquid or liquid to gas, for instance. Once the substance has changed states, then the temperature can start increasing again. The temperature of a substance is related to the speed of the substance's particles, or its kinetic energy. So when the temperature of the substance changes, the speed of the particles also changes. Take a look at this graph for the heating curve of water. This graph shows us what temperatures water is in the different phases and at what temperature water changes from one state to another. Looking at this graph, we can see that water is a solid at 0 degrees Celsius and below. It is a liquid from 0 to 100 degrees Celsius, and it is a gas from 100 degrees Celsius and above. That's what the red lines tell us on this graph. The blue lines on this graph represent when a phase change is happening. So, at what temperature will ice melt into water? You should see this happens at 0 degrees Celsius. At what temperature does water freeze into ice? This graph shows that this phase change also occurs at 0 degrees Celsius. Water will then evaporate into a gas at 100 degrees Celsius, and also water vapor will condense into a liquid at 100 degrees Celsius. The flat blue lines show that there is no temperature change while the substance is going through a phase change. Only after the phase change is complete does the temperature start to change again. Note that this graph only represents water. The temperatures at which other substances undergo phase changes is different for every substance. This next graph shows the relationship between energy, temperature, and particle movement. You can see how the particles are close together at the bottom of the graph where they are a solid, and then they spread out as they melt into a liquid and evaporate into a gas because they have more energy. The particles do the opposite if you move from the top of the graph downwards. They will get closer together and move less because they have less energy. In this video, you can see what happens to a metal ball when it is heated and cooled. We're going to click on the video to watch what happens. I like that video. I think it's pretty cool. So at room temperature, the metal ball fit through the ring, but as the particles were heated, they moved faster and pushed out with greater force. This can cause matter, like the metal ball, to expand. When the ball was heated enough, it did not fit through the ring. Then, as the ball was cooled in the water, the particles slowed down, they stopped pushing so much, and the metal ball got smaller. Then it was able to fit through the ring again. So here's a challenge for you to see if you can put together what you have learned in this presentation. 2 balloons are filled with an equal volume of air. One is put in the refrigerator for an hour, while the other is heated in a slightly warm oven. On your note taker, identify which balloon was placed in the refrigerator and which was placed in the oven, and explain how you know.